All right, we've gone from waves to electric fields here, and I guess electric current. That's kind of interesting, right? Anyway, this is uh, um, this is our formula for electric current. So that's I is current in amps, right? And electric current, what it's saying here is that the electric current is the amount of charge in coulombs, right, that passes by every second, right, or time in seconds, right? So that's our time, right? Okay, so just understand that literally an ampere is a coulomb per second, right? Is the same as, but also understand that it is not true that an ampere is defined as a coulomb per second. Okay, an ampere is defined in terms of you got two straight wires exactly a meter apart with exactly an ampere flowing in them, right? So it's the current flowing in each of two long, straight, parallel wires exactly a meter apart, such that there's a force of exactly 2 times 10 to the minus 7th newtons per meter of length. Okay, so that defines an ampere, and then literally this equation defines a coulomb as an ampere having flowed for 1 second, right? This is our Coulomb law, right? So if we have two charges, Q1 and Q2, and we know the distance separating their centers, right? Okay, this is Q1, Q2. Now that's our formula for that. R is that distance. K is either 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. And you can look that up in the front. It's the Coulomb constant. Or actually, K is defined, isn't a real constant, because K is really Boltzmann's constant, I'm just going to say. Okay, and that it's actually 1 over 4 pi epsilon naught. And epsilon naught is, what is that? I think it's 8.85 instead of minus 12 or something like that. I'll find it for you here. Okay, we got to get that right. We don't want to get that wrong. All right, and then the other one, the next one is the voltage. Voltage is the oh, here we go. Epsilon naught 8.85 times 10 to the minus 12th is exactly what it is. All right. And then this is our definition of voltage, right? So V is voltage. And then this is the work done on charge. Somewhere else there is a formula that says work is charge times change in voltage. It's exactly the same formula. And then in another place they've got potential energy is voltage times charge or something like that. These are all through the same exact equation. That's kind of fun, isn't it? All right, and then this is electric field, E field. Right, this is proper, although it gives me a rash that they write potential energy as an E like that. It should be PE in my opinion anyway. And then this is force over charge. Remember, this is the definition of electric field, right? It's how much force on how much charge, right? So electric field is in newtons per coulomb. It's also, by the way, in volts per meter as well. And then this is, this guy here is if we've got a wire, right? And we've got little charge carriers conducting down the wire, right? This N, that is the density, and this is charge carriers, the number of carriers per cubic meter in our case, because we're using meters as our area. This is area in square meters. This is velocity in meters per second, right? So notice it's meters squared times meters, and then we're going to do something that's inverse meters, right? And then this is kind of humorous, right? This is the charge on the charge carriers. Well, gee, aren't charge carriers, they're mostly they're electrons, right? So that's going to almost always be 1.602 times 10 to the minus 19th. I'm trying to think of some example where it wouldn't be that. I guess if you had like an ionic solution, if you had an ionic solution and you had a current flowing through there, literally those ions would move, and I suppose you could have like iron +3 or something like that, exotic. and then it would be 3 times that. I don't even know if that's real though. Anyway, so this basically this is our current, right? Okay, so this is the thing that allows you to calculate the amazingly slow electron drift velocity, right? The electrons move very slowly, and they just sort of meander, but they just sort of their path. This just gives us simply the component that's this way, right? So it'll do this random walk down the wire, but it's drifting this way as it goes, okay? And that is our current, and these things are slow. I think they're like sub-millimeter per second velocities for reasonably sized wires and currents, as I recall. I could be wrong about that. All right.